Mission Control, this is Astronaut Chowder. I've lost control of the guidance system. I'm being pulled in. The heat. Oh God, the heat shields are already at 40%. That thing, that massive red giant, it's like staring into the eye of a cosmic demon. If anyone can hear this, tell my story. Tell them what it's like to fall into the heart of a monster.
Welcome back, Cosmic Explorers, to the Cosmic Atlas, your gateway to the most mind-bending, awe-inspiring, and terrifying phenomena in our universe. I'm your guide through the cosmic unknown, and today we're attempting something absolutely insane. What you just heard was the final transmission from Astronaut Chowder, our brave and perhaps slightly unhinged explorer, as he embarks on the most dangerous mission ever conceived. His destination? RSGC1-F01. Not just any star, but one of the largest stars ever discovered by humanity. We're talking about a celestial behemoth so massive, so incomprehensibly enormous, that if you placed it at the center of our solar system, its surface would extend past the orbit of Jupiter. But here's the question that's going to haunt your dreams tonight. What would actually happen if you fell into this stellar giant? Would you vaporize instantly? Would you see the cosmic machinery of nuclear fusion with your own eyes before obliteration? How long would you survive, and what would those final moments feel like? Before we dive into this stellar suicide mission, I need you to do something for me. If you're ready to experience the most extreme environment in the known universe, if you want to witness scientific accuracy meet cosmic horror, then smash that like button right now. Subscribe to the Cosmic Atlas and hit that notification bell, because we're exploring the deadliest places in space, and you don't want to miss a single journey. Share this video with anyone who's ever looked up at the stars and wondered, what if? Today, Astronaut Chowder isn't just our narrator, he's our sacrifice to science. He's going to experience every excruciating, fascinating, reality-bending moment of falling into RSGC1-F01, and he's going to tell us exactly what it feels like. Because unlike other channels that just give you the cold, hard facts, we're living this experience together. Right, that's me, Astronaut Chowder, reporting for duty. When the folks at the Cosmic Atlas asked me to pilot this mission, I thought, how bad could it be? I've done EVAs, I've survived solar flares, I've even eaten space ice cream for 3 months straight. But now, looking at the mission brief, I'm starting to think I should have read the fine print. The mission is simple, Chowder. Well, simple to explain. Impossible to survive. Oh, that's comforting. You're going to approach RSGC1-F01 from 1 million kilometers out. You'll document every phase, the approach, the atmospheric entry, the descent through multiple stellar layers, and finally, the core, the nuclear fusion furnace where temperatures reach over 100 million degrees Kelvin, and where the very atoms that make up your body will be torn apart and reformed into stellar energy. I'd like to change my vote. Too late, Chowder. Your spacecraft is already locked on course. Autopilot engaged. No turning back. Well, if I'm going out with style. Let's show these cosmic explorers what it really means to touch a star. Engaging primary thrusters. RSGC1-F01. Here I come. Before we watch Chowder meet his spectacular demise, we need to understand exactly what he's falling into, because RSGC1-F01 isn't just big, it's a cosmic titan that challenges everything we thought we knew about stellar physics. RSGC1-F01 was discovered in 2009 by a team of astronomers studying the RSGC1 cluster, that stands for Red Supergiant Cluster 1, located approximately 20,000 light-years from Earth in the constellation Scutum. This cluster is special because it contains one of the highest concentrations of red supergiant stars ever found. It's like a retirement home for massive stars, all in their final bloated phase of life. So you're telling me I'm flying into a dying star? That's supposed to make me feel better? Actually, Chowder, that makes it even more dangerous. Red supergiants are stars in their death throes, having exhausted the hydrogen in their cores. They've expanded to enormous sizes, and they're incredibly unstable. But let's put the size of RSGC1-F01 into perspective, because your human brain literally cannot comprehend how big this thing is. Our sun has a radius of about 696,000 kilometers. It's big. It contains 99.86% of all the mass in our solar system. If Earth were a peppercorn, the sun would be a beach ball. But RSGC1-F01, its radius is estimated at 1,530 times larger than the Sun. That's approximately 1.06 billion kilometers in radius. Let me say that again, over 1 billion kilometers from the center to the surface. Okay, that's actually making me dizzy. Can you give me something I can actually picture? Sure, if you placed RSGC1-F01 at the center of our solar system, replacing the Sun, here's what would happen. Mercury, deep inside the star, vaporized. Venus, vaporized. Earth, vaporized. Mars, vaporized. The asteroid belt, vaporized. Jupiter, our solar system's giant, 11 times wider than Earth, would be inside this star or just barely at its surface, depending on the latest measurements. The surface of RSGC1-F01 would extend somewhere between 730 to 900 million kilometers from the center. Jupiter orbits the Sun at about 778 million kilometers. Let that sink in. So what you're saying is I could fit like, what, 1 billion Earths inside this thing? Try 4.5 billion Earths, Chowder, and that's being conservative. I'm gonna need a minute. You don't have a minute, but here's what makes red supergiants like RSGC1-F01 both fascinating and lethal. Temperature profile. Despite being called a cool star by stellar standards, RSGC1-F01's surface temperature is around 3,500 to 4,000 Kelvin, about 3,200 to 3,700 degrees Celsius. That's cooler than our sun's surface at 5,800 Kelvin, which is why it glows red instead of yellow. But don't let that fool you. Cooler is relative. It's still hot enough to vaporize any known material instantly. Density paradox. Here's the weird part. Despite being massive, red supergiants are actually less dense than our sun, especially in the outer layers. The outer atmosphere of RSGC1-F01 has a density comparable to a laboratory vacuum on Earth. It's more like falling through a hot ionized mist than hitting a solid surface. Wait, so it's not even solid? I'm falling into cosmic cotton candy? Deadly cosmic cotton candy that will disintegrate you at the atomic level, yes. The core, however, is a different story. The core has incredible density and pressure, fusing helium into carbon and oxygen, possibly even heavier elements. The core temperature exceeds 100 million degrees Kelvin. Composition. RSGC1-F01 is primarily hydrogen, about 73%, and helium, about 25%, with trace amounts of heavier elements, oxygen, carbon, neon, iron. These heavier elements are the products of nuclear fusion, the ashes of the star's burning life. So there's a chance it could explode while I'm inside? Astronomically unlikely, but technically yes. You know what? At this point, that might be a mercy. Okay, I'm reading 900,000 kilometers to stellar surface. Instruments are starting to pick up elevated radiation levels. Temperature outside the hull is rising. We're at 400 Kelvin and climbing.
Then let's begin our descent into hell, Chowder. Time to see what it really means to fall into the largest star ever discovered.
Initiating final approach. And hey, if I don't make it, tell my cat I left the tuna in the cupboard.
You're not making it, Chowder.
Right. Thanks for that. Okay, Cosmic Explorers, this is it. I'm currently 1 million kilometers from the surface of RSGC1-F01, and let me tell you, the view is absolutely unreal. Describe what you're seeing, Chowder. It's like, imagine the entire sky, everything you can see in every direction, just red. Not like a sunset red, but this deep, angry crimson that seems to pulse and boil. I can see massive darker patches on the surface. Sunspots, I guess you'd call them, but each one is larger than 10 Earths. There are prominences arcing up from the surface, these loops of plasma that extend for millions of kilometers. One of them just erupted while I was watching, and it was like seeing a solar tsunami launch into space. The radiation detectors are starting to go crazy. I'm reading X-rays, gamma rays, ultraviolet. Pretty much every type of electromagnetic radiation is slamming into my ship right now.
At 1 million kilometers, you are still relatively safe, Chowder, but let's talk about what's already beginning to happen. RSGC1-F01, like all stars, is continuously emitting radiation across the entire electromagnetic spectrum. From this distance, the radiation intensity is already thousands of times stronger than what Earth receives from the Sun. Your spacecraft's radiation shields are absorbing a tremendous amount of energy. Stellar wind. The star is also producing a stellar wind, a stream of charged particles, mostly protons and electrons, flowing outward at speeds of 10 to 40 kilometers per second. This wind carries mass away from the star, and RSGC1-F01 is losing mass at a prodigious rate. Estimates suggest up to 1/10,000th of a solar mass per year. That might not sound like much, but it's actually enormous. Our Sun loses mass at a 1,000,000 times slower rate.
I'm detecting the wind now. Particle density is increasing. The navigation computer is having to adjust course continuously just to compensate for the buffeting. It's like trying to drive through a hurricane.
Gravitational effects. You're also beginning to feel the gravitational pull of RSGC1-F01. Despite its lower density, it's still 20 to 40 times more massive than the Sun. At your current distance, the gravitational acceleration is relatively mild, but it's pulling you in inexorably.
Velocity is increasing. I'm at 15 kilometers per second and accelerating. At this rate, I'll cross the remaining distance in, calculates, roughly 19 hours. But something tells me I'm going to be going a lot faster by the end.
You will be. Gravitational acceleration compounds. As you get closer, you'll accelerate faster, much faster. Temperature rising. External hull temperature has now climbed to 800 Kelvin, about 527 degrees Celsius. Your heat shields are working, but they're beginning to warm up. Inside the cabin, you're comfortable at 293 Kelvin, 20 degrees Celsius, but the life support system is working harder than normal to dissipate the heat.
I can hear the cooling system ramping up. There's this constant hum now that wasn't there before. And the viewports have automatically darkened to protect my eyes. Even through the filters, that red glow is intense. It's like staring at a million campfires all at once. Your eyes would be permanently damaged without those filters. The brightness of RSGC1 from your current position is approximately 100,000 times brighter than a full moon as seen from Earth, and you're about to get a lot closer.
All right, so, what happens next? I mean, at what point do things get really dangerous? Honestly, Chowder, things are already dangerous, but you want to know when it gets obviously lethal. Do I? You're about to find out. You're approaching 100,000 kilometers. Welcome to the danger zone. I should have been a botanist. Botanists don't fall into stars. Okay, alarms. Why are there so many alarms? Computer voice. Warning, hull temperature critical.
Heat shield integrity at 72%. Radiation exposure exceeding safe limits. Structural stress increasing. Warning, warning. Computer, I know there are warnings. Tell me something I don't know. Narrator, what's happening? You've crossed into the zone where RSGC1-F01's environment becomes actively hostile to spacecraft. At 100,000 kilometers, roughly a quarter of the distance from Earth to the Moon, you're now experiencing conditions that no spacecraft in human history was ever designed to handle. External temperature. The hull temperature has skyrocketed to 2,000 Kelvin, 1,727 degrees Celsius. That's hot enough to melt aluminum, which melts at 660 degrees Celsius. Your spacecraft is made from advanced ceramic composites and carbon-carbon materials, similar to spacecraft heat shields, with a melting point above 3,000 degrees Celsius. But those materials are being pushed to their limits. The whole front of the ship is glowing. I can see it in the external camera feeds. It's like someone stuck my spacecraft in a forge. Radiation storm. The radiation intensity has increased exponentially. You're being bombarded by X-rays that would give you a lethal dose of radiation poisoning in minutes. Ultraviolet radiation intense enough to break apart DNA molecules. Charged particle radiation, protons and electrons moving at relativistic speeds. Gamma rays from the star's nuclear reactions. Your radiation shielding is absorbing most of this, but it's degrading. The atomic structure of the shielding material is being disrupted by the high-energy particles. Radiation levels inside the cabin are climbing exponentially. I'm at 5 sieverts cumulative exposure. That's already a 50% chance of death within 30 days if I somehow got out of here right now. You're not getting out, Chowder. Not helping. Electromagnetic chaos. The star's magnetic field is wreaking havoc on your electronics. Red supergiants have complex, tangled magnetic fields that cause massive loops and prominences of plasma to arc above the surface. You're flying through this magnetic maze, and it's inducing currents in your spacecraft systems. I just lost navigation. The gyroscopes are going haywire. The star's magnetic field is pulling at every piece of metal in this ship. I can feel it, like the whole spacecraft is vibrating. Velocity. You're now traveling at 45 kilometers per second, about 162,000 kilometers per hour. At this rate, you'll cross the remaining distance in, calculates, roughly 19 hours. But something tells me you're going to be going a lot faster by the end. You will be. Gravitational acceleration compounds. As you get closer, you'll accelerate faster. Much faster. Temperature rising. External hull temperature has now climbed to 800 Kelvin, about 527 degrees Celsius. Your heat shields are working, but they're beginning to warm up. Inside the cabin, you're comfortable at 293 Kelvin, 20 degrees Celsius, but the life support system is working harder than normal to dissipate the heat. I can hear the cooling system ramping up. There's this constant hum now that wasn't there before. And the viewports have automatically darkened to protect my eyes. Even through the filters, that red glow is intense. It's like staring at a million campfires all at once. Your eyes would be permanently damaged without those filters. The brightness of RSGC1 from your current position is approximately 100,000 times brighter than a full moon as seen from Earth, and you're about to get a lot closer. All right, so, what happens next? I mean, at what point do things get really dangerous? Honestly, Chowder, things are already dangerous, but you want to know when it gets obviously lethal. Do I? You're about to find out. You're approaching 100,000 kilometers. Welcome to the danger zone. I should have been a botanist. Botanists don't fall into stars. Okay, alarms! Why are there so many alarms? Computer voice. Warning. Hull temperature critical. Heat shield integrity at 72%. Radiation exposure exceeding safe limits. Structural stress increasing. Warning. Warning. Computer, I know there are warnings. Tell me something I don't know. Narrator, what's happening? You've crossed into the zone where RSGC1-F01's environment becomes actively hostile to spacecraft. At 100,000 kilometers, roughly a quarter of the distance from Earth to the Moon, you're now experiencing conditions that no spacecraft in human history was ever designed to handle. External temperature. The hull temperature has skyrocketed to 2,000 Kelvin, 1,727 degrees Celsius. That's hot enough to melt aluminum, which melts at 660 degrees Celsius. Your spacecraft is made from advanced ceramic composites and carbon-carbon materials, similar to spacecraft heat shields, with a melting point above 3,000 degrees Celsius. But those materials are being pushed to their limits. The whole front of the ship is glowing. I can see it in the external camera feeds. It's like someone stuck my spacecraft in a forge. Radiation storm. The radiation intensity has increased exponentially. You're being bombarded by X-rays that would give you a lethal dose of radiation poisoning in minutes. Ultraviolet radiation intense enough to break apart DNA molecules. Charged particle radiation. Protons and electrons moving at relativistic speeds. Gamma rays from the star's nuclear reactions.
Radiation levels inside the cabin are climbing. I'm at 5 sieverts cumulative exposure. That's already a 50% chance of death within 30 days if I somehow got out of here right now. You're not getting out, Chowder. Not helping! Electromagnetic chaos. The star's magnetic field is wreaking havoc on your electronics. Red supergiants have complex, tangled magnetic fields that cause massive loops and prominences of plasma to arch above the surface. You're flying through this magnetic maze, and it's inducing currents in your spacecraft systems. I just lost navigation. The gyroscopes are going haywire. The star's magnetic field is pulling at every piece of metal in this ship. I can feel it, like the whole spacecraft is vibrating. Velocity. You're now traveling at 45 kilometers per second, about 162,000 kilometers per hour. At this speed, you're crossing distances equivalent to Earth's diameter every 4.5 minutes, and you're still accelerating. The gravitational acceleration at your current distance is approximately 0.02 times Earth's gravity. That doesn't sound like much, but it's continuous and it's increasing. Within the next few hours, you'll be experiencing multiple Gs of acceleration. I can see the stellar wind now. It's not invisible anymore. There are actual streams of glowing plasma flowing past the ship. It's beautiful and terrifying. Some of these streams are as wide as Earth. What you're seeing is ionized gas, plasma, heated to tens of thousands of degrees. The density has increased to the point where it's visible. You're essentially flying through the star's extended atmosphere now. Solar prominences. And you need to watch out for those prominences, Chowder. Those loops of plasma you mentioned earlier. They can erupt with little warning, releasing the energy equivalent to millions of nuclear bombs. If you fly into one, don't finish that sentence. I'll just navigate around them. Except, oh wait, my navigation is fried. What was that? Structural stress. Your spacecraft is made of multiple materials, metals, ceramics, composites. They're all expanding at different rates due to the extreme heat. The thermal expansion is causing the structure to warp and bend. The hull integrity is down to 55%. The computer says I have maybe 2 hours before catastrophic failure. How far to the surface? You're still 80,000 kilometers out, Chowder, and you're about to enter the chromosphere, the lower atmosphere of the star. That's when things get truly impossible. Truly impossible? What's been happening for the last hour? A mild inconvenience? Comparatively, yes. Time dilation. Here's something else you should know, Chowder. Due to the intense gravitational field, time is beginning to move differently for you than for an observer far away. It's a tiny effect at this distance. We're talking microseconds, but it's measurable. As you get closer to the core, where gravity is strongest, this effect will become more pronounced. Your clock and the universe's clock are starting to drift apart. Oh, fantastic. So not only am I being cooked alive, irradiated, magnetically scrambled, and crushed, but time itself is getting weird? This just keeps getting better. I'm not gonna lie to you, Chowder. The next phase is going to be exponentially worse. You're about to cross the boundary into the star itself. The chromosphere awaits. Okay, I signed up for this. I'm a scientist. I'm an explorer. This is the ultimate frontier. If I'm gonna go out, I'm gonna document every single second of this for the Cosmic Atlas viewers. This is for science. I'm scared. You should be. Crossing stellar boundary in 10, 9, 8, 7, 3, 2, 1. I'm in. I'm actually inside the star. Welcome to the chromosphere, Chowder, the lowest layer of RSGC1-F01's atmosphere. You've just crossed from interplanetary space into the actual body of the star. Everything is red. I can't see anything else. The external cameras are almost useless. It's like flying through a red fog, except the fog is made of superheated plasma. Temperature. The external temperature has jumped to 5,000 Kelvin, or 4,727 degrees Celsius. This is hotter than the surface of our sun. Your heat shields are ablating, burning away layer by layer. The spacecraft is shedding material like tears of molten metal. Hull integrity just dropped to 30%. The computer's saying I have maybe minutes before catastrophic failure. And it's hot. Even inside the cabin it's getting hot. I'm at 40 degrees Celsius in here. The cooling system is at maximum capacity and it's losing. The chromosphere of a red supergiant is a chaotic place, Chowder. The density has increased dramatically. You're now flying through matter that, while still far less dense than Earth's atmosphere, is dense enough to interact with your spacecraft like a physical medium. Atmospheric density. At this level, density is around 10 to the -7th kilograms per cubic meter. That's still 1,000,000 times less dense than Earth's air at sea level, but it's 1,000,000,000,000 times less dense than the space you were in just minutes ago. And every particle of that air is ionized plasma moving at thousands of kilometers per hour. The ship is shaking violently. I'm getting thrown around the cabin. The turbulence is insane. You're experiencing the star's convection currents, massive flows of hot plasma rising from the interior and cooler plasma sinking back down. These currents are planetary in scale. Imagine the updrafts and downdrafts in a thunderstorm, but each current is larger than Earth and moves at supersonic speeds. Plasma seas. What you're flying through isn't a uniform atmosphere. It's a roiling, churning sea of ionized gas. Temperature fluctuates wildly, from 4,000 to 6,000 Kelvin depending on whether you're in a hot rising plume or a falling cool stream. I just flew through something that felt like hitting a wall. Temperature spiked to 6,500 Kelvin for 3 seconds. The outer hull layer is gone. I'm down to the secondary heat shield. Magnetic mayhem. The magnetic field here is incredibly tangled and strong. Magnetic field lines are being twisted by the convection, creating temporary but powerful magnetic structures. These are accelerating charged particles to enormous energies. I just saw lightning, stellar lightning. A bolt of electricity the size of a continent just arced past my ship. If that had hit me, you'd be vaporized instantly. Those discharges carry more energy than all of Earth's lightning storms combined across a year, released in a fraction of a second.
I can smell something burning. The cabin is filling with smoke. The life support system just failed. I'm breathing in toxic fumes from melting insulation.
Your cabin pressure is dropping, Chowder. The hull has microfractures now. Superheated plasma is finding its way inside.
Pressure at 0.3 atmospheres and falling. Temperature inside is 80 degrees Celsius. I'm burning my hands on the controls. I need to seal my suit. Suit sealed. I've got 30 minutes of oxygen. That's not going to be enough, is it? No, Chowder, but you won't need 30 minutes. One of the things you signed up for was to report your experiences until the very end. Keep your channel open as long as you can. I can see
There's a darker region ahead. Redder. Denser. That's the photosphere, the visible surface of the star, the region where the star becomes opaque to visible light. You're about to plunge into it. I can feel it. My skin is burning, even inside the suit. Everything hurts. Is this what dying feels like? You're experiencing the early stages of radiation poisoning and thermal injury, yes. Your nerve endings are being destroyed. Soon you'll feel nothing. I'm scared. I don't want to die. I know I signed up for this, but I'm not ready. I'm not... Hull breach. Catastrophic failure. Structural integ... The ship is breaking apart. The spacecraft has failed, Chowder. The hull has ruptured. You're being exposed directly to the chromosphere's environment. I'm in free fall. The ship is gone. It's just me and this suit, and this red hell. Your suit is rated for space. It's designed to protect you from vacuum and moderate radiation. It was never designed for this. The outer layers are already burning away. Suit temperature critical. The cooling system is overloaded. I'm at 70 degrees Celsius inside. I can't breathe. It's too hot. Falling into the depths. You're no longer traveling in a ship, Chowder. You're falling as a human body, wrapped in a rapidly failing spacesuit through the atmosphere of the largest star ever discovered. Gravity is pulling you down, accelerating you further. You're going to punch through the photosphere and descend into the convection zone. I see light, bright light below me, like a floor of fire rising up to meet me. That's the photosphere, isn't it? Yes. What happens when I hit it? You don't hit it, you pass through it, into something far worse. I'm sorry I wasn't braver. Tell the Cosmic Atlas viewers, tell them it was beautiful. Terrible, but beautiful. The biggest star in the universe, and I'm the only human who ever got to see it from the inside. Here it comes. I'm still alive. How am I still alive? You're not, Chowder, not really. But you're conscious. Your brain is still receiving signals. You have seconds, maybe a minute at most, before complete system failure. Tell us what you see. It's like being inside a living thing. The plasma. It's moving, flowing. There are currents of light and dark. Columns of... I don't even know what to call them. Plasma tornadoes? Each one is wider than Jupiter. They're carrying material up and down in this endless cycle. You're in the convection zone, the region where energy from the core is transported outward through physical motion of the plasma itself. In our sun, the convection zone is only about 30% of the star's radius, but in a red supergiant like RSGC1-F01, the convection zone extends almost to the core. Temperature around you has reached 100,000 Kelvin, 99,727 degrees Celsius. At this temperature, there is no solid matter, no liquids, only plasma, the fourth state of matter. Electrons have been stripped from atoms, creating a soup of free ions and electrons. My suit it's melting. No, not melting, vaporizing. I can see pieces of it turning into gas, just disappearing. My arms. I can see my arms through the suit. The material is becoming transparent as it's destroyed. Your body temperature has risen above 100 degrees Celsius. Water boils at this temperature. Your water in your cells is boiling. Your blood is boiling. Your brain is being cooked. Can't feel my hands. Can't feel anything. Just heat. Everything is heat. The nerve endings that transmit pain have been destroyed. You're going into hyperthermic shock. Your body's regulatory systems have completely failed. As you fall deeper, the plasma density is increasing. You're now in matter that's about 1,000th the density of water. That still sounds thin, but compared to where you were, it's becoming substantially thicker. The drag on your body is slowing your descent, but not enough. You're still falling at over 100 kilometers per second. Colors. I see colors that shouldn't exist. Ultraviolet? No, beyond that. My eyes are seeing radiation they weren't designed to see. Everything is glowing. My hands are glowing. Am I glowing? Yes, Chowder. Your body is now hot enough that it's emitting thermal radiation in the visible spectrum. You're literally glowing red hot. Organic molecules are breaking down all over your body. The proteins that make up your muscles, your organs, your brain, they're being ripped apart at the molecular level. DNA double helices are unwinding and shattering. The organized structure that is astronaut chowder is being reduced to its constituent atoms. I can hear something. A sound. Deep. So deep. Like the universe is humming. What you're perceiving isn't sound. Sound can't propagate the same way in this environment. You might be sensing the massive electromagnetic oscillations in the plasma, or perhaps your auditory cortex is misfiring as it dies. Or maybe you're hearing the star itself, the collective vibration of trillions upon trillions of tons of plasma in motion. Magnetic field chaos. The field here is extraordinarily complex. Field lines are twisted, braided, and constantly shifting. You're being bombarded by charged particles accelerated to near light speeds by these magnetic fluctuations. Every atom in your body is being hit by cosmic rays of the star's own creation. I'm not afraid anymore. It's strange. I feel peaceful. Like I'm becoming part of something bigger. The star. It's singing. I can hear it. It's beautiful.
You're experiencing the final stages of consciousness, Chowder. Your brain is dying, but in its last moments, it's trying to make sense of the incomprehensible stimuli. Some call it euphoria. Others call it the brain's last mercy. The pressure around you has increased to over 100 atmospheres. The pressure you'd experience a kilometer beneath the ocean on Earth. But unlike water, this pressure is from superheated plasma, and it's crushing you from all sides. Your body is being compressed, going deeper. So bright, can't see, can't think. Am I still me? The philosophical question of consciousness at the moment of death. Are you still astronaut Chowder? Or are you becoming something else? A scattered collection of atoms on their way to being incorporated into the stellar fusion cycle. The energy density here is immense. Every cubic meter of space contains enough thermal energy to power a city for a year, and you're falling through it, your body absorbing that energy, being overwhelmed by it. The turbulence is beyond description. You're being tossed between rising plumes of superheated plasma and falling rivers of relatively cooler material. Each transition subjects your body to forces equivalent to tens of thousands of Gs, though at this point, your body is more of a concept than a cohesive reality. Mom, I see home. Earth. It's so blue, so small. I'm sorry I left. I should have stayed. I should have... You're hallucinating, Chowder. Oxygen deprivation, thermal damage, radiation poisoning. Your brain's visual cortex is firing randomly, creating images from memory. Time dilation. Time is moving even more slowly for you now. The gravitational field is stronger. For every second you experience, the outside universe experiences 1.001 seconds. It's a tiny effect, but it's real. You're traveling through space-time differently than the rest of the universe. The final plunge. Ahead of you, if ahead has any meaning in this chaos, is the core, the region where temperatures reach 100 million degrees, where nuclear fusion transforms hydrogen into helium, helium into carbon, carbon into heavier elements. The cosmic forge, the heart of the star. I see light, pure light, white, gold. It's calling me. I'm not scared. I want to go. I want to see. Take me. The core awaits, Chowder. The final transformation. From astronaut to atoms. From matter to energy.
From human to star, thank you for watching Cosmic Atlas. Keep exploring. Astronaut Chowder's consciousness has faded. His biological body, what remains of it, is no longer capable of thought, sensation, or communication. But we will continue his journey, following the atoms that once comprised a human being as they descend the final distance to the core of RSGC1-01. Distance to core, 10,000 kilometers. Temperature, 10 million Kelvin. At this temperature, atoms as we understand them don't exist. Even the toughest atomic bonds are broken. Everything is fully ionized plasma. Nuclei and free electrons, all moving at incredible speeds, colliding constantly. The atoms that were once astronaut chowder are completely gone. The carbon, hydrogen, oxygen, nitrogen, calcium, phosphorus, the elements of life now exist as individual atomic nuclei surrounded by clouds of free electrons. The carbon that was once part of Chowder's DNA disintegrated. The calcium that gave his bones strength ionized. The iron in his blood reduced to nuclei. Pressure, 10 billion atmospheres. This is pressure beyond any earthly experience. The core of Earth reaches about 3.6 million atmospheres. We're now in pressures 3,000 times greater than the center of our planet. At these pressures, matter behaves in exotic ways. The plasma is so compressed that quantum mechanical effects become important. Electrons are packed so tightly that they obey Fermi-Dirac statistics, creating what's called electron degeneracy pressure in certain conditions. Density. The density has risen to approximately 10 kilograms per cubic meter, about 10 times less dense than water. But remember, this is ionized plasma at 10 million degrees. The mean free path, the average distance a particle travels before colliding with another particle, is measured in nanometers. Collisions are constant, transferring energy in all directions. Energy transport. At this depth, energy is being transported by three mechanisms: convection, physical movement of plasma, though this is weakening as we approach the core; radiation, high-energy photons, X-rays and gamma rays are constantly being emitted and absorbed, creating a random walk of energy; conduction, direct transfer of kinetic energy through particle collisions; radiation pressure. The radiation pressure here is immense. Photons carry momentum, and when you have an unimaginable number of high-energy photons bouncing around, they create an outward pressure. This radiation pressure is one of the key forces that prevents the star from collapsing under its own gravity. Gravitational crushing. Speaking of gravity, the gravitational acceleration here is approximately 10 times Earth's surface gravity. But this isn't felt as a directional pull. Everything is in free fall towards the center, and the pressure is isotropic, equal in all directions. The atoms that were once astronaut chowder are being compressed, pushed towards the center by the weight of the entire star above them. Nuclear reactions begin. At these temperatures and pressures, nuclear fusion reactions are beginning to occur around what was once chowder. Not in his atoms, his hydrogen nuclei, protons are being swept along towards the core where fusion happens. But in the surrounding plasma, hydrogen is fusing into helium. The PP chain reaction. Two protons fuse to create deuterium, heavy hydrogen, releasing a positron and a neutrino. Deuterium fuses with another proton to create helium-3, releasing a gamma ray. Two helium-3 nuclei fuse to create helium-4, releasing two protons. Each reaction releases energy according to Einstein's famous equation, E equals mc squared. The mass lost in these reactions is converted to energy, the energy that powers the star, that creates the heat and light that Chowder experienced as he fell. Distance to core center, 1,000 kilometers. Temperature, 50 million Kelvin. Pressure, 100 billion atmospheres. The final descent. The atoms that were once astronaut chowder, approximately 7 times 10 to the 27th atoms, 7 octillion atoms, are now scattered across a region several kilometers wide, mixed inseparably with the stellar plasma. They're falling at speeds approaching 1,000 kilometers per second due to the immense gravitational pull. Time dilation is now significant. For the external universe, time is passing about 0.2% faster than for our atoms. If an outside observer could somehow watch Chowder's atoms fall, they would appear to be moving in slow motion as they approach the core. The core boundary. The core of RSGC1-01 isn't a hard boundary like a planet's surface, it's a gradual transition. The region where the temperature and pressure become high enough for the primary fusion reactions to occur at significant rates. This region is estimated to be several million kilometers across in this massive star. Distance to core center, 100 kilometers. Temperature, 100 million Kelvin. Pressure, 500 billion atmospheres. The fusion furnace. We've reached it. The core, the heart of RSGC1-01, the place where creation happens, where elements are forged, where Einstein's equation becomes viscerally, violently real. Welcome to the center of a star.
This is it, the core of RSGC1-F01, the nuclear fusion engine that powers one of the largest stars ever discovered, a place where the laws of physics create, destroy, and transform matter in ways that seem almost magical, but are purely, terrifyingly real. Temperature, 100 to 150 million Kelvin. To put this in perspective, the surface of the Sun, 5,800 Kelvin. The core of the Sun, 15 million Kelvin. The core of RSGC1-F01, 100 million Kelvin plus. This is temperature at a level where thermal energy per particle approaches the binding energy of atomic nuclei. This is where matter itself is transformed. Pressure, 500 billion to 1 trillion atmospheres. The weight of the entire star, tens of solar masses, is pressing down on this core. The density here is approximately 100 kilograms per cubic meter, about 100 times the density of water, but this is plasma at 100 million degrees. What happens to Chowder's atoms? The hydrogen atoms, protons, that were once part of astronaut Chowder's body are now in the fusion zone. Here's what happens. Proton-proton fusion. The protons that were once in Chowder's water molecules, his proteins, his DNA, they're colliding with other protons at tremendous speeds. Normally, protons repel each other due to electromagnetic force, like charges repel, but at these energies and with quantum tunneling effects, occasionally two protons get close enough for the strong nuclear force to overcome the electromagnetic repulsion. When this happens, two protons fuse. One proton converts to a neutron, releasing a positron, an antimatter electron, and a neutrino. Deuterium, heavy hydrogen, is formed, and energy is released. This deuterium quickly fuses with another proton, creating helium-3 and releasing a gamma-ray photon. Mass-energy conversion. In each fusion reaction, a tiny amount of mass is converted to energy. Approximately 0.7% of the mass is converted, according to E equals mc2. This doesn't sound like much, but consider the speed of light squared, c squared, is 9 times 10 to the 16 meters per second squared. This is a huge number, so even a tiny amount of mass, say the mass of a few protons, releases an enormous amount of energy when multiplied by c squared. The energy that was Chowder. Let's do some mathematics. Astronaut Chowder's body mass was approximately 75 kilograms. About 10% of that was hydrogen, roughly 7.5 kilograms. If all of Chowder's hydrogen underwent fusion, which it won't all at once, but over time as it circulates in the core, it would release E equals 0.007 times 7.5 kilograms times 3 times 10 to the 8th meters per second squared. E, approximately 4.7 times 10 to the 16 joules. That's 47 petajoules. To put that in perspective, the atomic bomb dropped on Hiroshima released about 63 terajoules. Chowder's hydrogen, if fully fused, would release energy equivalent to about 750 Hiroshima bombs. One human body, 750 nuclear weapons worth of energy. The carbon, oxygen, and other elements. Chowder wasn't just hydrogen. He was carbon, 18% of body mass, oxygen, 65%, nitrogen, 3%, and trace amounts of heavier elements. In the core of RSGC1-F01, which is in the Red Supergiant phase, helium fusion is also occurring. 3 helium-4 nuclei fuse to create carbon-12, the triple alpha process. Carbon-12 confused with helium-4 to create oxygen-16. Further reactions create neon, magnesium, and even heavier elements. The carbon and oxygen atoms that were chowder are actually the products of stellar fusion from earlier generations of stars. They were forged in stars that exploded billions of years ago. Now, they're back in the stellar crucible, potentially being incorporated into even heavier elements. Neutrino production in the core produces vast numbers of neutrinos, ghostly particles that barely interact with matter. Neutrinos created right now in the core of RSGC1-F01 will pass through the entire star and escape into space within seconds, carrying information about the nuclear reactions directly from the core. Some of the protons that were chowder, when they fuse, will produce neutrinos. These neutrinos will race through the star and out into the galaxy. In a sense, part of chowder, or at least the information about what happened to him, will escape the star at the speed of light, spreading out into the cosmos. Time dilation at maximum. Time dilation in the core is at its maximum for this star. Due to the intense gravitational field, time here moves about 0.5% slower than far from the star. This means if you could somehow watch the core from a safe distance, chemical reactions and processes would appear to be happening in slow motion. The life of a core atom. An atom, or rather a nucleus, there are no atoms as such here, in the core doesn't stay there forever. The core is dynamic, with convection and turbulence mixing material. Over thousands to millions of years, nuclei from the core get mixed into the outer layers and eventually ejected into space through the stellar wind, or ultimately in a supernova explosion. Chowder becomes starlight. The energy released from the fusion of chowder's hydrogen doesn't instantly appear as light. It's created as high-energy gamma rays in the core. These photons begin a random walk outward, being absorbed and re-emitted trillions and trillions of times. Each time a photon is absorbed by an atom and re-emitted, it loses a bit of energy, shifting to longer wavelengths. The journey of a photon from the core to the surface of RSGC1-F01 takes an estimated 100,000 to 1 million years. The photon scatters, bounces, gets absorbed and re-emitted, gradually working its way outward. By the time it reaches the surface, the high-energy gamma ray has been converted to visible light and infrared radiation. That red glow that Chowder saw as he approached the star, that light was created in the core, possibly millions of years ago, and has been gradually making its way outward through countless absorption and emission events. The ultimate transformation. Astronaut Chowder came to RSGC1-F01 as a human being, a complex arrangement of organic molecules, cells, organs, consciousness, and dreams. He fell through the stellar atmosphere, was broken down into atoms, and finally, in the core, transformed into energy and helium. His matter has been scattered, his energy has been released, the organized complexity that was Chowder has been returned to the cosmos in its simplest forms. In a poetic sense, Chowder has become part of the star. His atoms will circulate in the convection currents, his energy will eventually emerge as starlight, and millions of years from now, when RSGC1-F01 reaches the end of its life and explodes as a supernova, some of Chowder's atoms will be ejected into space at a significant fraction of the speed of light. Those atoms might eventually become part of a nebula, then collapse into a new star system, possibly forming planets, maybe even contributing to new life forms. In the end, astronaut Chowder didn't just visit the largest star, he became part of the cosmic cycle. From stars, through life, back to stars, and perhaps to life again. We've watched astronaut Chowder's journey from astronaut to atoms, from matter to energy. We've descended through the largest star ever discovered and witnessed the cosmic forces that govern creation and destruction at the most fundamental level. But what does it all mean? What happens next to the star that consumed our brave explorer? The future of RSGC1-F01. RSGC1-F01 is in the Red Supergiant phase, which means it's in its late stages of its life. It's already exhausted the hydrogen in its core and is now fusing helium into heavier elements. This phase is relatively brief in cosmic terms, perhaps a few 100,000 to 1,000,000 years. The fusion cascade. As the core runs out of helium, it will contract and heat up, eventually becoming hot enough to fuse carbon, then oxygen, then neon, magnesium, silicon. Each successive fusion stage is shorter than the last because heavier elements release less energy when fused. The silicon fusion stage, the final stage before catastrophe, lasts only about 1 day.
Eventually, RSGC1-F01 will create an iron core. Iron is the most stable nucleus. Fusing it doesn't release energy, it requires energy. When the core is iron, fusion stops. The core collapses in less than a second. The collapse is halted by neutron degeneracy pressure, creating a neutron star. The outer layers, no longer supported, collapse inward and then bounce off the incompressible neutron core, creating a shock wave that tears through the star. RSGC1-F01 will explode as a Type II supernova. The explosion will be visible across the galaxy. For a few weeks, RSGC1-F01 will outshine billions of normal stars combined. The energy released will be equivalent to all the energy the star produced during its entire main sequence lifetime, compressed into a few seconds. And in that explosion, all the elements that were forged in the core, including the atoms that were once astronaut Chowder, will be ejected into space at 10% the speed of light. Those atoms will mix with interstellar gas and dust. They'll form nebulae, glowing clouds light years across. Gravity will pull regions of these nebulae together, forming new stars. Some of those stars will have planetary systems. The atoms that were Chowder might end up in a planet. They might end up in an asteroid, an ocean, a mountain, or perhaps in another living being somewhere in the distant future. This is the cosmic cycle. Stars are born from gas clouds, live their lives fusing lighter elements into heavier ones, and die in explosions that seed the galaxy with those heavier elements. New stars form from the enriched gas containing the products of previous generations. Every element in your body heavier than hydrogen was forged in a star. The iron in your blood, the calcium in your bones, the carbon in your DNA, all created in stellar cores and supernova explosions. You are, quite literally, made of star stuff. Chowder's contribution. Astronaut Chowder added his mass, his atoms, his elements to RSGC1-F01. In the grand scheme of the cosmos, it's an infinitesimal contribution. The star loses more mass to its stellar wind every few seconds than Chowder contributed in his entire body. But symbolically, Chowder has joined the cosmic cycle.
He's become part of the machinery of creation that has been running since the first stars formed over 13 billion years ago. Through our journey with Chowder, we've explored the incredible scale of red supergiant stars, the layers of stellar atmosphere, chromosphere, photosphere, convection zone, the physics of temperature, pressure, and density in extreme environments, nuclear fusion and the creation of elements, radiation, electromagnetic effects and plasma physics, time dilation and relativistic effects in strong gravitational fields, the transformation of matter to energy according to Einstein's equation, the life cycle of massive stars and their ultimate fate. All of this is real science. This is what actually happens in stars throughout the universe. The details might vary. Different mass stars behave differently. Different composition affects the fusion pathway, but the fundamental processes are the same. So what if you fell into the largest star, RSGC1-F01? You'd be subjected to the most extreme environment imaginable. Radiation would kill you within minutes. Heat would vaporize your body within seconds of entering the chromosphere. Pressure would crush you. Turbulence would tear you apart. And in the core, you'd undergo the ultimate transformation. Your atoms would be fused, creating energy according to the most famous equation in physics, contributing to the light and life of the star itself. You wouldn't survive, but in a sense, you'd become immortal, your atoms spreading through the galaxy, potentially becoming part of new worlds, new life, new possibilities. That's the beauty and the terror of the cosmos. It's bigger than us, more powerful than us, and utterly indifferent to us. But we're part of it, made from it, destined to return to it. And that, Cosmic Explorers, is what would happen if you fell into RSGC1-F01, the largest star ever discovered. From the first warnings at 1,000,000 kilometers out, through the hellish descent through the stellar atmosphere, to the final transformation in the core's nuclear furnace, we've experienced the ultimate cosmic journey with astronaut Chowder. Let's take a moment to remember what we've learned today. RSGC1-F01 is incomprehensibly massive, 1,530 times larger than our Sun, with a volume that could contain over 4 billion Earths. Red supergiants are in their death phase. Having exhausted core hydrogen, they've expanded enormously and are fusing heavier elements, marching towards a supernova explosion. The environment is immediately lethal. Even at 100,000 kilometers, spacecraft fail. At the stellar surface, everything vaporizes within seconds. Stellar atmospheres are dynamic and violent. Convection currents the size of planets, magnetic storms, plasma turbulence, and temperatures from thousands to millions of degrees create an environment beyond our most extreme nightmares. The core is where creation happens. At 100+ million degrees and trillions of atmospheres of pressure, nuclear fusion transforms hydrogen into helium and beyond, converting mass to energy according to E=mc². We are made of stars. Every heavy element in our bodies was forged in stellar cores. We are the universe experiencing itself. How does falling into RSGC1-F01 compare to other cosmic death traps? Falling into the Sun, much faster death. The Sun is smaller, denser, and you'd reach lethal zones quicker. But the Sun's core is only 15 million Kelvin. Falling into a white dwarf, incredibly dense, you'd be crushed by gravity and simultaneously incinerated. White dwarfs have surface gravities 100,000 times Earth's. Falling into a neutron star, instant spaghettification. The tidal forces would stretch you into a stream of atoms before you even got close to the surface. Neutron star surfaces have gravity billions of times Earth's. Falling into a black hole depends on the size. For a supermassive black hole, you'd survive past the event horizon before tidal forces killed you.
For a stellar mass black hole, you'd be spaghettified long before reaching the event horizon. RSGC1-F01 offers a uniquely slow death. You have time to experience the descent, to witness the stellar machinery, to understand what's happening. It's simultaneously the most beautiful and the most terrifying way to die in space. Our journey today raises profound questions. What does it mean to be human when faced with such cosmic enormity? Our lives are brief flashes in cosmic time. Our planet is a mote of dust in an incomprehensibly vast universe. And yet, we have consciousness. We can understand nuclear fusion. We can comprehend our own insignificance and still find meaning. Astronaut Chowder, our fictional explorer, faced his death with fear, yes, but also with curiosity, and ultimately with acceptance. He documented his experience for future generations. He contributed to human knowledge, and in the end, he became part of something greater than himself. That's what exploration means. That's what science means. We push boundaries, we ask, what if, and we pursue answers even when those answers are uncomfortable or frightening.
Before you go, I need you to take action right now. If this journey through the largest star in the universe amazed you, educated you, or terrified you in the best way possible, slam that like button. Your likes tell YouTube that cosmic content matters, that scientific accuracy combined with engaging storytelling deserves to be shared. Subscribe to the Cosmic Atlas and become part of our community of cosmic explorers. We're diving into the most extreme, bizarre, and mind-bending phenomena in the universe: black holes, neutron stars, dark matter, the edge of the observable universe, in scenarios that will make falling into RSGC1-F01 look like a vacation. Hit that notification bell so you never miss our next cosmic adventure, and share this video with anyone who's ever wondered about the stars, anyone who appreciates science, anyone who wants to understand their place in the cosmos. What if you were trapped on the planet with the most extreme conditions ever discovered? I'm talking about a planet where it rains molten glass sideways, where 1 year lasts 40 Earth hours, where the day side is 2,500 degrees Celsius and the night side is deep freeze territory. We're going to visit HD 189733b, and we're taking our brave explorer to experience exoplanet hell. You won't want to miss it. Look up at the stars tonight. Those points of light are suns like RSGC1-F01, burning through their nuclear fuel, creating the elements that make up everything around you. You're not separate from the cosmos. You're not just in the universe. You are the universe, a part of it that's become conscious, that can look back at itself and understand. That's incredible. That's beautiful, and that's why we explore. In memory of astronaut Chowder, explorer, scientist, and the only human to ever experience the core of the largest star, his atoms now dance in the stellar winds of RSGC1-F01, waiting to begin their next cosmic journey. This has been the Cosmic Atlas. I'm your narrator, and we'll see you in the next journey through space, time, and the incredible phenomena that define our universe. Until then, keep exploring, keep questioning, and never stop looking up.